Good evening. If you can hear me, just chuck something in the chat window so you can hear me and say you can hear me okay. That would be a good start. And since there's only 2 people here, you can introduce yourselves as well. Be a very targeted revision session. Feel free to chuck something in the chat window when you can hear me. If you can't hear me, then I may need to sort that out. Let me know if you can hear okay. It would be useful. Hear okay. Okay, I've just checked that. That looks like that's working. There's a couple of people online. So over on the right hand side, you've got the chat window. You can add some questions into. Feel free to add whatever you want in there. There's only a few people online, so depending on whether anybody else logs in or not, we can kind of take this step by step. We'll go over data representation. I know it said CPU on the list, but we haven't done data representation in a while, so binary and all that sort of stuff. So I'll have a quick look through some of that. If you want to introduce yourself in the window over on the right hand side, if you're on, depending on what device you're on, you can do. You might need to go through to YouTube to do that. If you've gone through Google Classroom, it might not have popped up. So you might want to click on the link and go through that way. Otherwise, I will make a start while there are a couple of people online and go from there. Right. So if we look over the spec and see what the spec says in terms of what's required for data representation, there's some stuff about number bases. There's stuff about converting between number bases. There's stuff about units of information, a bit of binary addition, binary arithmetic, shifting some binary. And then we've got stuff to do with character encoding, representing images, representing sound, data compression. I think that's about it. Yeah, that's it. So it's quite a big pick, and it can fall under paper 1 and paper 2. It doesn't necessarily have to fit under one of those, and it could appear in both, or different parts could appear in both as well. So we tend to find that there is always a binary question of some sort on the paper at some point. So it's well worth making sure you know your binary stuff when you get into the exam. So we'll start off with this one to start off with. Number bases. Understand the following number bases. You've got decimal, binary, and hexadecimal. So you've got 3 that they want you to know. So a decimal number are just your numbers 1 to 9, 6, 7, 8, 9. So any number that you might be used to. So that's 237 or 128 or 5. Any of those are decimal or base 10 numbers. Then binary. Binary is 1s and 0s. So that is a binary number. That is a binary number. Anything where there's only 1s and 0s is a binary number. You've got 2 options, which is why it's called base 2. Your 2 options are 1 or 0. The reason why it's base 10 is you've got 10 options, including 0. So then hexadecimal, base 16, means you've got 16 different options. So that's 0 to 9, 5, 6, 7, 8, 9, A, B, C, D, E, F, plus A, B, C, D, E, F on the end. And A is represented by 10, or represents the number 10 in decimal. B is 11, C is 12, D is 13, E is 14, and F is 15. So we've got, again, 16 different characters we can use there. That's hexadecimal base 16. It then says, understand that computers use binary to represent all data and instructions. Well, that's kind of a given. Students should be familiar with the idea that a bit pattern can represent different types of text, images, sound, and integers. So what this is meaning is that we can use this binary to represent lots of different things, hence the word data representation. Explain why hexadecimal is often used in computer science. So this is hexadecimal. Hexadecimal is a lot easier for humans to be able to read and understand than binary, because we can represent a much bigger number using hexadecimal rather than representing it with lots of 1s and 0s. So that's the main reason why we use hexadecimal. It's much easier for humans to read and understand. So that's your first bit into number bases, the first 3 in there. Then it says converting from number bases. So if we start with understanding how binary can be used to represent whole numbers. So that means that we can take a number, something like, we can do it both ways. So if we take a binary number, so that is an 8-bit or a byte of binary. It's a byte because it's 8 bits, 8 bits in a byte. And we can then turn this into a decimal number by writing the numbers over the top: 1, 2, 4, 8, 16, 32, 64, 128. So we've now got our numbers written across the top, which represents each of our different values. So when we've got a 1, it means we want one of those. So we want a 2, we want a 4, we want a 8, and we want a 64. So we can add those up together. So that's 78. So we can then make that 78, which is our decimal number. If we go back to sort of our number bases, that is a base 2 number, 78, and this, I'm sorry, that's a base 10 number, and this is a base 2 number, and we can convert between them as we go. We can go the other way as well. So if we have the number, I don't know, 150, let's go for 150, we can then plug that into our binary, a byte of binary. So if we write out our numbers again, 32, 16, 8, 4, 2, 1, we can then convert these between each other. So we can kind of go, we want one of those. So we want 150, we're going to take 128. So if we take off 128 now, that leaves us with 22. So that leaves us with 22 left. So we can't use a 64 because that's too big. We can't use a 32, that's too big. So we're going to use a 16. So now we can then take 16 off of this, which then leaves us with 4, 5, 6. So that leaves us with 6 left over. Well, that's too big, so we can't use one of those. We can use a 4 though, so we take a 4 off of there, which then leaves us with 2. We want a 2, which leaves us with nothing, so therefore we don't need a 1. And then we can represent our number 150 using a binary value in that way. So that's understand how binary numbers can be used to represent whole numbers. Students must be able to represent decimal values, these decimal values, using a binary number and vice versa. So you need to be able to convert these back and forward. When you get into the exam, this should be simple to remember. You just double each time as you go. A lot of mistakes people make are down this end. Just make sure you're kind of doubling each number and making sure you're writing out the correct numbers as they go. And a byte of binary should go from 1 to 128, because if you put ones in every single column, the total will be 255, because then the next number over here will be 256 if you had another bit on the end. But we don't need that because we've only got a byte of binary, and you need to be able to represent the numbers, as it says, between 0 and 255, which is why you need to be able to do those different values in there. Cool. Understand how hexadecimal can be used to represent whole numbers as well. And students must be able to represent decimal values between 0 and 255 in hexadecimal. And then it says here you've got to be able to convert between all of them as well. So if we go into how we've got a hexadecimal number, so let's go for hexadecimal value AB. Now with hexadecimal values, we know that everything in base 10, everything in this column's worth 1, everything in that column's worth 10, and everything in that column's worth 100. So if you had the number 237, that's how we can read that number back. When we have it in binary, we have everything in these columns being worth 4, 2, and 1. So if we had this number, we would know that that's a 4 plus a 1, so that would be 5 in total. But when we come on to hexadecimal, we know that everything in this column is worth 16, and everything in this column is worth 1, because we can have up to 15 characters in the first column before we then need to move into the next column, move into the 16 column and move on. When you're converting numbers, you only need to use 2 values in hexadecimal, because you can represent 0 to 255 using 2 characters. And we'll have a look at that in a minute. Now we've got these different values in here, we now need to work out what they represent. So A, we remember from doing this over here, A is worth 10, or is equivalent to 10 in decimal. So we can do A is 10 and B is 11. So we can do 1 times 11 is 11 plus 16 times 10, which is 160. And then we can add those together, 171. So we know that the hexadecimal value AB is actually the number 171. So that's how we can use hexadecimal numbers to represent decimal values, and vice versa. You can reverse the process going that way if you need to. The only other thing that you might need to do is you might need to be able to convert, it says binary and decimal, which we've done, binary and hexadecimal, and decimal and hexadecimal. So this is decimal and hexadecimal, whereas you might need to do the binary version as well. Binary actually makes things a lot simpler. So if we take our value 171, and we go try and convert it back the other way and show this working. So if we write out our values and turn it into binary, 32, 16, 8, 4, 2, 1. So 171, we want to then work out what this is in binary. So you can have a quick go in your head and see whether you can work out what the binary is. Remember, start at this end and work our way down. So will we need 128? Well, yes. So if we do 171, take 128, we want one of those. That leaves us with, I'll write it down here, 171 take 128, leaves us with 43 is left. So we can't use one of those, that's too big, but we do need a 32. So if we then take 32 off of this amount, so we then take off 32, that leaves us with 11 is left. So this is now too big, so we can put a 0 in there. Then we can say we do want an 8, so we then take off an 8, and then we take an 8 off of the value of 11, which gives us 3. Sorry, I've gone off the bottom, which gives us 3. So we can then write in here, we can put a 0 in there because we don't need a 4, and we need a 1 and a 1 in there because we need the values 2 and 1. So we've then, let's just move that out of the way. We've then kind of converted our decimal value into binary. But what we want to do now is we want to split this up. So if we look at this, what we can do is we can convert this really quickly into a hexadecimal value by splitting it into 2 nibbles. A nibble is 4 bits, so it's just a byte of binary split in half. And over this side, we can leave this as we are, so 8, 4, 2, 1, and we can add this up. So 8 plus 2 plus 1 is 11. And we know that in hexadecimal, 11 is the value B. If we come over this side, obviously these are too bigger numbers, so we're going to replace these with 8, 4, 2, 1 again for our other character of hexadecimal, and then we can add these together. 8 and 2 is 10. Therefore, we know in hexadecimal, 10 is represented by the letter A. So that's how everything kind of links together. This binary value is 171, which then links to this hexadecimal value in here. So we'll do one more, just for the purpose of practice. I'll give you another value. So let's do, I don't know, let's pick the value 207 is our value, 207. So first thing I would do is I would convert that into binary. That's probably the easiest thing we can do to start off with. 16, 8, 4, 2, 1. So we've got our number 207. So to convert that into our binary number, we do the same thing as we've done before. We take the number and we need to say we need one of these, 128. So 207 take 128. Leaves us with 79. So we can use a 64 this time. So 79 takes 64, leaves us with 15. 64 leaves us with 15. So we don't need one of those, we don't need one of those, and we're left with 15. So we do need an 8. So we can take 8 off of 15, which then leaves us with 7. And then to make the number 7, we know we need a number 4, because we can then take 4 off, which then leaves us 3 left, and we know that 2 and 1 is 3. So we can just add those onto the end. So we've now got our binary value, as we've got it there, and we can now convert into hexadecimal really easily. So we can take this number, we can split it down the middle, and then we can do 8 plus 4 plus 2 plus 1. Well, that adds up to 15. And if we then look at our letters in this sheet over here, we know that 15 is represented by the letter F. If you start off from A being 10. So 15 is F, so we can put that over that side. And then over this side, we need to change these numbers, 8, 4, 2, 1. We've got 8 and 4, which we know is 12, and 12 in there. And we know from our sheet over here that 12, if we start with A being 10, 12 is C. So the answer to this one, if we have the number 207, we now know 207 equals 11001111 in binary, but it also equals CF in hexadecimal. So we've now converted between the three, and you can convert either way you want to in there. Just to double check our working, we can even go one step further, and we know, remember from CF, we remember everything in this column is worth 16 and everything in this column is worth 1. We know the letter F is 15, and we know the letter C is 12. We did that up there, 15 and 12. And then we can times these together. So 16 times 12, any of you maths people out there, 16 times 12 is 192 plus 15, because it's 1 times 15, gives you the answer 207, which interestingly equals the number that we've got written at the top. So that's how everything links together, and that's how we can calculate binary and hexadecimal and make that work. Cool. Moving on. Let's go back to here. So understand how binary numbers can be used. We've done that one. Understand how hexadecimal numbers can be used to represent decimal numbers. We've done that one. Be able to convert in both directions, binary to decimal, decimal to hexadecimal, binary to hexadecimal. So using this technique over here, using these sort of easy techniques, these are the ones I would suggest you remember, because then you can get it into every single combination you need to. If you're given a binary value, you can convert it into hexadecimal and convert it back to a decimal number. If you're given a decimal number, you can convert it into hexadecimal really easily by turning it to binary first of all. I would suggest if you're going to do that way, it's easier to convert it into binary first and then turn it into a hexadecimal value. So using this sort of toolkit, you can kind of convert it in any direction you need to. Okay, so we've done that one as well. Next one, units of information. Know that a bit is a fundamental unit of information. A bit is represented by a 0 or a 1. Well, we've just done our binary calculations, and that's sort of where we started with that. And a byte is a group of 8 bits. That's what we said up here. A group of bits up here is those 8 bits are a byte. Be aware in the exam, you could be given a value that is 7 bits long. That technically is not a, well, it is not a bit of information, but when you come to do the hexadecimal stuff, you always start on the right-hand side, no matter what. So if you're converting it into a decimal value, you always start on this side being 1, 1, 2, 4, 8, 16, 32, 64. We do not have 128 in this version. And if you're doing the hexadecimal version, you're splitting it down the middle, but you're splitting it this side. So you start off this side, count 4, 1, 2, 3, 4, split. 1, 2, 3, right, you haven't got anything else. Technically, if you want to make it a bit easier for yourself, you can just put another 0 on the front, because it just means that there's no other 0 to go into that space. So that's just a word of warning. But in here, it says a byte is a group of 8 bits, and that's where that comes from. So we can kind of tick that one off. Then we've got these prefixes and things. Know the names and symbols and how they correspond, and sort of you need to know from a kilo up to a gigabyte. And it says over here, students might benefit from knowing that the terms kilobyte, megabyte, etc. have been used to represent powers of 2. There's other sort of measurements in here as well. What they will, and there's kibibytes and all that sort of stuff. Students do not need to know these, so I wouldn't panic about these. I would focus on this bit over here. This is the most important bit that you need to know. So 1 kilobyte, 1 megabyte, 1 gigabyte, 1 terabyte. Each of those is 1,000 bytes bigger than the last one. So 1 kilobyte is 1,000 bytes. 1 megabyte is 1,000 kilobytes. So if you're converting between them, I've got this piece of paper here. If you're converting between them, and you need to, let's say you've got 3,000 bytes, you know that 3,000 bytes is actually 3 kilobytes. Make sure you get the little k in kilobytes. Every other one is bigger, but there's a little k for kilobytes. You can also then know that if we said we had 3,000 kilobytes, that would then equal 3 megabytes, and so on. And you can then convert between the two. If we had 3 gigabytes, we can then divide that by 1,000 as well, and we can do 0.003 terabytes, because we've kind of divided it in that way. So you can work these out in whichever way you want to. You can convert between different values, but the way you will probably use this more is where we get onto images and sound a bit later, and you're giving a really long number that you convert sort of, let's say you convert a number that's like 34 million I'm just going to make a number 84271 bits. Bits is a really sort of, that's way too long. We don't like storing information in bits, and we don't refer to file size in bits. So we want to convert that into bytes to start us off with. We know that there are 8 bits in a byte, 1 byte. So what we can do is we can take that value and we can divide that by 8 to get that into our value. So I'm going to quickly do that on the calculator. 34384,271 divided by 8 is, oh, no, I didn't type that in right. Apologies. 34384,271 divided by 8 is 4298033. Again, that's really big. That's, why did that divide? That didn't really divide right. What have I done wrong? 34384,271 divide by 8. 298033. 123. Yeah, that's right. Sorry. Yeah, 34 million, 4 million. I've got too many numbers. So 4 million in there. So we've now got 4 million bytes. Again, that is way too big to work with. We wouldn't refer to a file size as 4 million bytes. So then we want to divide it down. So we would then divide it by 1,000. So we would then get rid of the ones off the end, and we would then have 4,298, we'll round up, kilobytes. Again, that's way too big because we can then get it down even smaller. If we divide that by 1,000, we're then ending up with 4.29 megabytes. And that is then a more manageable size that we can then work with. So that's sort of how you work from bytes into sort of kilobytes and megabytes and move them around. Okay, so that's that one there. Converting between kilo, giga, and terabytes. That's the ones you need to know the different sizes. Next one, binary arithmetic. Binary arithmetic, sorry. You'll need to add 3 binary numbers together. Students will need to add together up to 3 binary numbers using a maximum of 8 bits per number. You're only expected to add together a maximum of 3 ones in a single column. Answers will be a maximum of 8 bits in length and will not involve carrying beyond the 8 bits. So that's kind of handy that we know that, because that means that it's not too complicated a binary maths question that you have to do. So let's give these a go. Let's come up with a binary number, and obviously I don't know whether this is going to do carry bits and all that sort of stuff, because I'm just going to make up a random number of 8 bits. 0 0 0 0 1 1 0 1 0 1 1 0. Okay, so the way we can kind of make this work and sort of understand it a little bit more before we look at this, if we have the number 0 and 0 in our decimal values, we know that equals 0. When we have the number 1 and nothing, it represents the number 1 in decimal values. When we have 2 ones as a decimal value, we know that equals the number 2. However, we can't represent in binary the number 2, so we represent it using the binary 1 0. So if you remember back to where we were converting between decimal and binary, that everything in that column's worth 1, everything in that column's worth 2. So we know that. When we've then got 3 ones, we know in a decimal value that is a number 3. Again, we can't represent that using binary. So what we do instead is we convert it into binary. Everything in that column's worth 2. Everything in that column's worth 1. And then it does say you only need up to 3. And we'll come back and we'll do a 4th bit if we need it in our example in a minute. But that's sort of how you do everything up to 3 bits when you're adding up 3 bits in a column. So over here, if we start off with this one, we start on the right hand side all the time. So there we've got 1 plus 0 plus 0. Well, we know as a decimal number that is 1. And again, 0 plus 0 plus 1, again, that's 1 as a decimal number. Then we move on to this column and we've got 1 and 0 and 1. Now that should equal a 2, but we can't write that in binary. So if we look down here, we have a 1 and a 0. So we put a 0 in here and we carry a 1, because you can see here it's got 1 and 0, and we sort of carry that like so. That then means we then look at this whole column here and we see how many ones we've got in this column. And again, we've got a 1 and a 1. So a 1 plus 1 is 2. So we would then put a 0 in this column and we would then carry a 1. Now, for the purpose of this, I don't want to do 4 bits. So I'm just going to change this one to be a 0. There we go. Right. Now in this column, we have a 1 and a 1 and a 1. So we have 3 ones, which we now get a chance to use this down here. So it's a 2. Everything in this column is worth 2. Everything in this column is worth 1. So we're now going to put a 1 in our kind of column here and the 1 underneath. So that's 1, 1. You can kind of see it written there. 1, 0, 1, 0. Okay. Then everything in this column, we look again, we've got 2 1s again, so that's going to be a 0 in this column, and we're going to move a 1 into that column because we've got our 1 and our 0. And then in this column, we now have 3 1s again, which is there. So we then put a 1 in that one, and we carry a 1 over to this one because we've got 1 1. Remember, the bit on the left is the bit that we carry. And then in this one over here, we will have a carry bit in this one, and I know you won't have that in the exam, but we've now got 3 1s again, so we're going to put a 1 in here. And if we then run out of space, it's then just going to be added onto the end as an extra carry bit, and a bit of an overflow error because we've gone above our value of our byte. We've gone out. We've got 8 bits here. We need a 9th bit to go up to the next value. Now, what you could do to make sure it works is you can convert each of these into a decimal number, and then you can convert this one into a decimal number, and then you can check that all these 3 add up to this decimal number, and you can make sure it makes sense. If you have time in your exam, it's well worth doing just to double check you've done it completely right, and that you've been doing the right thing with this. But if you don't, then this is probably the quickest way to be able to just do your binary addition as you go through. So that's how you can then convert some binary numbers, or add together binary numbers to give you your total binary number using binary arithmetic. So let's go back to here. Be able to add up 3 binary numbers together using a maximum of 8 bits. That's what we've just done here. Okay. Let's just very quickly do one more, just in case that one didn't make any sense. But we're going to do it a little bit shorter because you never know what the exam will give you. 0, 0, 1, and then we're going to do 1 in there, and we're going to do 1 in there, and 0, 1, 0. Let's go with that. So there's your 3 binary numbers again. We're not going up to 8 bits this time, but we can still do our binary arithmetic, and we can go in here. That's 1 in that column. That one there, we've got 2 1s, so we do a 1 and a 0, 1, 0. Then we've got 3 1s in this column, so we do a 1 and carry the 1. And then we have 2 1s in this column, so we do a 1 and a 0. And then we have 2 1s in this column, so we're going to do a 1 and a 0. So although we have a carry bit onto the end of this one, we technically haven't got an error because we still have less than a byte of binary in this example. Okay, that's how we add binary numbers together. So we're going to tick that one off. That one's done. Right, let's keep going. There are no questions yet. If you've got any questions, chuck them in the question window over on the right-hand side. That's the idea behind the live stream. So I'm not talking to myself. If you want to do anything in particular, then shout. Otherwise, I'm just going to keep going with some of the spec and go through each of the different areas in the spec. So be able to apply a binary shift to a binary number. Expected to use a maximum of 8 bits. You're expected to understand and use a logical binary shift. You don't need to use fractional representation, and you'll need to describe situations where those binary shifts are used. So if we look at what binary shifts are, we can shift binary to the left or the right, and depending on whether we're moving it to the left or the right, we're timesing or dividing by 2 as we shift it. So if we have a number that looks a little bit like this, so we know that 1, 2, 4, 8, 16. So we know that that number there equals the number 20. So if we shift this number to the left, we do 1, 0, 1, 0, 0. And then because we're shifting it to the left, we add another 0 on the end. So it's a left shift. We now know that everything in this column is 32 plus 8. So this one now equals 40. So the process of shifting it once to the left-hand side times is everything by 2. So every time we shift to the left, we're multiplying our value by 2. If we take this original number at the top and we now shift it one place to the right, so we're now moving that to there, that to there, that to there, that to there, and we're getting rid of a 0 off the end, we can then see what this adds up to. 8 plus 2 is 10. So every time we shift it to the right, we know that we are dividing by 2. We're doing that mass calculation every time we times it to the right. If we have a number that looks a little bit like this, and we now need to shift it to the right-hand side, and we get a question that says, shift it to the right by 2 spaces, we're going to move this to the right, and we're going to get rid of those two, and we'll just end up with the number 101, and we'll get those two are not relevant anymore. So we will then end up with this value instead. This used to be 1, 2, 4, 8, 16. So this used to be 16, 4, 23. Now we've shifted it across. This is 4, that's 1. So we've now got it as 5, because 23, hang on, we've done it wrong. 16, 4 is 23. And then we've shifted it 4 and 1 is 5. Oh yeah, so sorry, we've shifted it by 2 spaces. So that's dividing it by 2 and then dividing it by 2 again. So dividing that by 2 would have given us 11.5, but obviously we can't get that in binary, and then shifting it again, dividing that by 2 is then giving us the value 5, because technically that divided by 2 is sort of less than 6, 5 point whatever it is. So that's why we work out with those different values, and we just keep them whole values instead. So shifting to the right divides things by 2, shifting to left times everything by 2 as you move through. That's sort of your binary addition, binary shift, and describe where they can be used. Well, it's multiplication and division. That's sort of what we've just gone over there in terms of everything. Character encoding. So this is really important for when you're looking at binary and things like that. So understand what a character set is and be able to describe the following character methods. So 7-bit ASCII and Unicode, and we'll be able to convert characters to character codes and back the other way. So 7-bit ASCII. 7-bit ASCII says that we have the values 1, 2, 4, 8, 16, 32, 64, and we don't use 128 because we've got 7 bits. And what that means is we can then use the binary values of 7 bits to represent a decimal number. So we've got the value 42 in this scenario here. And then that 42 will represent a letter in ASCII, which I don't know off the top of my head, but let's just imagine that that letter is B there. If we then had a question that said convert the number 44 into an ASCII letter, you don't actually have to do the binary calculation or anything. All you need to do is go B, C, D, because it's a couple of letters after the B. So you just need to work out sort of your alphabet and work through that way. It is a 7-bit code. So if they ask you what ASCII is a 7-bit character code, whereas Unicode allows you to use a lot more bits. It doesn't actually say anything about extended ASCII anymore, I don't think. But extended ASCII, if you need to know, is 8 bits. So you can add another bit on the end, and that will allow you to represent more character codes. Obviously, if you're using 7 bits, the maximum sort of the numbers that you can represent are everything from 0 to 127. Because if you made these all ones, that would add up to 127, which means that you can have 128 characters. Because if you've got the value 0 and then everything up to 127, that gives you 128 characters you can use with ASCII. If you've got something like extended ASCII or Unicode or anything like that, if you add another bit on the end, you can represent the number 0 to 255. If you add another 1 up there, which then means you can represent 256 characters. So by adding another bit, you can double the amount of characters that you can represent. Unicode then lets you represent a lot more letters, up to sort of millions, basically, depending on how much, what sort of Unicode character set size you're going to use and how many bits you're going to use. I think down here it says you don't need to know about UTF-8 and UTF-16 or other versions of Unicode, but you do need to know it's representing using more characters. So if there's a question about 7-bit ASCII only gives you a range of characters, what could you use? Unicode allows you to then run more character sets in different languages and represent other bits and pieces that you might want to be able to use on the computer. Understand that character codes are commonly grouped and run in a sequence. So this is what we're talking about here. Character codes work so that everything is in a sequence: B, C, D, and then you can work it out. If I give you the letter G, you could then work out that that would then be represented by, well, 44 is D, 45 is E, 46 is F. That must mean 47 is G, and work it out that way. Students should know that character codes are grouped together and they run in a sequence. That's what you said there. So A is actually 65. So if we were using the proper numbers, we would then work with A being 65 and go through there. The pattern also applies for other groupings such as lowercase letters and digits. That's a really horrible one that they sometimes do, and they give you like a multiple choice, and they go, if A is 40, no, what is it in there? A is 65. Which of these, C, F, D, which of these is represented by the number 66? Well, and then you'll look at that list and go, oh, B is represented by the letter 66. Well, no, technically that is wrong. It's the capital letter B, because the capital letter A is represented by the number 65. And that's how you can then tell. So be aware of that one. That's a trick that they sometimes play, that you've got to then make sure you spot that, because the character sets go in order based on their numbers, in that sort of order. Describe the purpose of Unicode and the advantages of Unicode over ASCII. So obviously we were talking about this before. You can represent more characters and different languages using Unicode by increasing the amount of bits that you can use. However, if you do increase the number of bits you use, obviously the file size gets bigger, because you've got to represent each character using more bits. Know that Unicode uses the same codes as ASCII up to 127. Well, what that means is we've said here that A is represented by 65. That would be the same in ASCII or Unicode. So it doesn't matter what you use, A is always the number 65. Unicode just allows for more usage and more characters after that instead. Yeah, symbols allowing a far greater range of characters. So that's what you would say if it asks you why you'd use Unicode over ASCII. Right, representing images. Keep powering through. Understand what a pixel is and be able to describe how pixels relate to an image and the way the images are described. Students should know that a pixel is short for a picture element and is a single point in a graphical image, or a square of color is also what I'd say in that. It's a square of individual color. So VDUs, or visual display units, display pictures by dividing up the pixels into thousands and thousands arranged in rows and columns. So what it is saying is a screen is made up of loads of different squares of color that you then represents one image. So that one's green, that one's green, that one's green, that one's green, that one's green. So this is sort of my grass in my image, and then these pixels up here might be blue because that's my sky, and they're all connected together, and they represent different colors. So that's what a pixel is. So it's a setup of millions of different of these sort of pixel squares to put an image together. So a bitmap is a map of bits to represent our image. So we've now got to be able to take this and convert it into bits so that we can then store it in the computer. We can't just store a grid of squares in the computer. We need to store it in binary. Describe the following for bitmaps: the size in pixels and the color depth. Know that the bitmap image size is the pixels width times the height, and is known as the image resolution. So the number of bits that you have, the number of pixels that you have in an image represents the resolution. So the more pixels you have in your width and your height, the better. So in HD, I think it's something like 1280 by 1080, I think, something like that. Can't remember off the top of my head. But there's that many pixels going that way, there's that many pixels going that way. So the quality of your image will be higher because you've got more pixels regardless of the size of the screen. So they might just be smaller squares if it's a smaller screen, but you still have that amount of pixels on the screen. So that is the image resolution, how many pixels that you have. The size of the image is expressed by saying the width and the height of the pixels. So that's that. So we work that one out. So let's say that's our pixel size. So we times that by that, which would then give us how many pixels we have in our image. So we have 1280 times by 1080 gives us this number. Let's put the commas in. 1,382,400 pixels in our image, in this example image that we've got here. And then that's how we can work out how many the size of our image, basically how many pixels we've got within our image. Color depth is the number of bits used to represent each pixel. So this is then the next step to working out how big our image is, depending on how many colors we've got. So if we have an image that is either a black or a white pixel, we then either have two options. So we would represent, let's say, that one with a 1 and that one with a 0. Therefore, that is a 1-bit color, 1-bit image, because that's represented by 0 and that's represented by 1. So we're only using 1 bit to be able to represent the two colors in there. So 1 bit equals 2 colors. However, when it gets a little bit more complicated, we might want to use, let's say, 3 colors. So we have a green, and then we have a pink, and we might have a black. Doesn't really matter what the colors are. Pink and a black. This one, we can't now represent it just using 0 and 1 because that's only 2 options. So we now need to use 2 bits. So we'd have 0, 0, 0, 1, 1, 0. Now, actually, we could have a 4th color over here being 1, 1 because we're using 2 bits. So if we're using 2 bits, we can represent up to 4 colors. And so on. If we then have more colors and we represent it using 3 bits, my question to you is, how many colors can we have? Let's work it out. So you've got 3 bits. You can have 0, 0, 0 as 1 color, 0, 0, 1, 0, 1, 0, 1, 0, 0. And we can have all of these different combinations. They're all the different combinations of bits we can have. So therefore, we can have 1, 2, 3, 4, 5, 6, 7. Uh-oh, I missed something. What did I miss? 0, 1. Uh-oh, what did I miss? 0, 1, 1. That's what I missed. 0, 1, 1. Yep. So 1, 2, 3, 4, 5, 6, 7, 8. 8 colors with 3 bits. So that's how we can then represent more colors using different bits. So let's say, for example, we need 3 bits. Or actually, let's go back to this example. Let's say our image is made up of these colors only. So blue, green, pink, and black. And we need 2 bits to represent each of our different colors in our map up here. That means that each of these squares will be represented by 2 bits, a bit like paint by numbers, like that. If I give you the numbers, you'd be able to paint those colors in. So therefore, we know that if all of these pixels is worth 2 bits, we now need to take the amount of pixels, we need to times it by the amount of bits that we're using, and that will give us how many bits in total we need to use. So that will give us roughly, let's go for 2, I'll write out the whole number anyway. There you go. That is the number of bits we need to use to represent our whole of our image, because it's 2 per square. If we needed 3 bits, obviously we then times it by 3, or 4 bits, we times it by 4, and that's how we can calculate the file size. Now, if we go back to the conversation that we had earlier, we don't like leaving things in bits. We need to convert it into bytes to make it easier to understand. So we take that number, and the first thing that we need to do is divide it by 8. Which then leaves you with 345,600 bytes. Again, rubbish number, divided by 1,000 to give you your value, 345 kilobytes. That was close, kilobytes. Again, we don't, you could leave it there. It depends. 345 kilobytes is fine, or you can divide it by 1,000 again, and you could say 0.34 megabytes is another way. So it's up to you. It depends how they ask for the question to be answered, depending on what you're doing. And that's sort of how you represent images. Describe how a bitmap represents an image using pixels and color depth. So you've got to be able to describe what this color depth is, how many colors you can use, which is what we've talked about here, and the bit depth, how many bits you can use. So you need to be able to describe this thing over here that I've just gone through. Describe using examples how the number of pixels and color depth can affect the file size of a bitmap image. So the more pixels that you have, or the more colors that you have, the higher the file size. Because obviously, if you need more bits to represent more colors, that's going to increase that. And if you need more pixels, then that's obviously going to increase that. And all of these numbers will then increase, which will increase the number of bits you're using, which will increase your file size. So if you increase the amount of pixels and increase the color depth, that is going to increase the file size. Calculate the bitmap image file size. Well, that's what we've just done there. It is the width of the image, the height of the image, and the color depth in bits. Convert binary data into a black and white image. So what that means is if you're given an image of 0, 1, 0, 0, 0, 1, 1, 1, what it's saying is that's represented by white, that's represented by black. So draw me the image in here. If you're given all the pixel boxes to fill in, well, that one's going to be black. And those last 3, well, that one's going to be white, that one's going to be white, that one's going to be white. And the last 3, I've got enough grid, are then going to be black. So you just need to be able to look at a binary list of numbers and then represent it using zeros and ones for black and white. They will identify and they will say 1 is black, So make sure you read the question really carefully, and they'll tell you which way around to do. Convert a black and white image into binary data. Well, that's just back the other way. If you're given an image that looks a bit like this, and that one's black, and that one's black, and that one's black, well, then it would be 0, 1, 0, 1, 1, 0, like so. And literally as simple as that. You don't have to do anything more complicated. Just read it back and convert it into zeros and ones. So we'll tick that one off in there. Understand that sound is an analog and must be converted into digital form for storage. So let's do a quick bit on sound. Take another bit of paper. So we know that a sound wave looks a little bit like this. And this is an analog wave. We can't store this in the computer, so we need to convert it into a digital form, into a digital sound recording, or ones and zeros to be able to save it on the computer. Understand that sound waves are sampled to create a digital version of the sound. So to do that, we need to take samples of this wave. So we specify how many samples we are going to take over this wave over 1 second of time. And in my example here, we're taking 1, 2, 3, 4, 5, 6, 7. We're taking 7 samples, which actually isn't very many, because we usually work in something like 44,000 samples per second. So hertz here stands for samples per second. And that's what we'll need in our calculation a bit later. So actually, in my example here, I have 7 hertz. I'm taking 7 samples per second. Understand that the sample is a measure of amplitude at that point in time. So when you're asking what a sample is, you are recording the amplitude of the wave. And that could come up as a question. So that's worth knowing. Let's take that one off. Done. Describe in the digital representation of sound in terms of sample rate and sample resolution. Sample rate is the number of samples taken a second, measured in hertz. That's what I've just talked about there. Sample resolution is the number of bits of the sample. So once we've taken the sample, we now need to represent this using bits. So over here, we would then create our what they call it, sample resolution over here, the number of bits, and we would then represent this using a number of bits. So everything there is that, and then represent that using that, that using that, and so on. We would then say, actually, we can then record this. That is 0, 0, 0. That one there is 0, 1, that one there is that. And we can then record our wave using our bits that we've recorded, that we've kind of read off of the analog wave. We've then got in here, we can then use this to store our data. So we can then just record this on the computer because we can store that. And we can then draw back our wave once we finish by putting it back into the grid and reading it out in that way. The sample resolution is the number of bits per sample. So the more bits you have, the closer this gets together, the more accurate the wave can be represented. So if I doubled the amount of bits, and let's say I took it to 6 bits, for example, then we would have a much finer line in between, and therefore each sample would be represented using 6 bits. But in doing that, we're going to increase our file size because we now need to, each sample is now represented by more bits. So this is your sample resolution down here, depending on how many bits that you have. And then your amount of samples goes across the bottom there, which then brings us on to calculating the file size. We need to know that the file size is the rate of bits. So the rate that we've got going on here. So in this example, it's 7 hertz, 7 samples, times by the resolution, which in this example, let's say is 3. Ignore that I went bigger, but it's 3, times by the length of the track. So if we do that on the back, so I had 7 samples times by 3 samples times by 3 bits per sample times by a track of 60 seconds. It's got to be in seconds. That will give us how many bits in total our track is. So we do 7 times 3 times by 60. That gives 1,260 bits for the whole of our track. Again, we don't like bits, so we'll then turn it into bytes by dividing it by 8. That gives us 157.5 bytes. And then let's turn it into kilobytes just for the sake of it, because it will probably be a lot bigger. But anyway, 0.15 kilobytes. So this track here, if it was recorded like this and it had 7 samples, and that was a sample rate, and that was the amount of bits that they were using, it would take 0.1 kilobytes to store that on the computer. What's worth knowing as well is that when you increase the sample resolution or you increase the amount of samples per second, obviously the amount of data that's going to be used to store it goes up, because you're having to store more bits and you're storing more samples in your wave. The idea is that when you've then stored it as this, you can then take it and you can then, when you play it back through the computer, you can reform that wave when you want to, and you can take the binary values and reform it. The only thing is, if you don't take enough samples or your sample rate's not big enough, when you come to redraw out the wave, it will then not look anything like it, because the samples will be taking a best guess of where they are, which is why the sound quality is affected by your resolution and how many samples that you take. So you can say that even though you've got to balance that file size, you can take millions and millions and millions of samples and millions using millions of bits, but that will make your file size huge and pointless. So you've got to balance it between the two. Data compression. Explain what data compression is. Understand why data may be compressed. So we compress data to save space on our computers, or for transferring across the internet, or for streaming. Loads and loads of different reasons why we might, I'm trying to find some paper, might compress our data. And there are different ways we can compress data. We can, I'm sure it says here, did it say about lossy and lossless? No, it doesn't. Okay, we'll do it anyway. Lossy and lossless, two different types of compression. And there are different ways that we can compress data. We can either compress data and then be able to uncompress it and get it back to its full sort of original state, or we can compress data and we can't then uncompress it back to its full state. So let's take an image, for example. We can only use lossy compression. So I'm going to do lossy first with images or video or sound. Let's say we've got an image where there's like loads of green pixels and then there's the odd black pixel between them. What that would then mean is the compression algorithm would go, actually, we're going to ignore this one in here, and we're going to then say, actually, we have one black one, and then we have 5 green pixels, because they're just generally nearly all the same. Ignore that one, we can just turn that one into green. If we do that, when we come to take that compression, this is our compressed version. When we come to uncompress it, we then have a problem, because we never knew that that other black one existed within there. So we've then come to uncompress that data. So we can't get it back to its original state. Whereas lossless, if we had, let's go back to the image example. If we had this one and we still had this problem and we compressed it, we can still compress this using a form of compression, and we then would store it as one black, 2 green, 1 black. We'll do that in a different pen. 1 green, 1 black, 2 green. That's technically still compressing it in some sort of way. Whether you save any space, not sure. But you can then regain, we can put that back together again once we're finished, because we can read that back. It's better with text, because you need to then get all your text back when you uncompress it. Whereas with images, it doesn't necessarily matter as much. So you've got lossy and lossless compression very, very quickly there. Why is it desirable to compress data? Like we said, we want to save space. We want to make it easy to transfer over the internet. Great for streaming. Loads and loads of different examples we've got there. Understand how you can compress using Huffman trees and calculate the number of bits for Huffman trees. We'll do that one in a minute. And RLE frequency plans. We'll do that one. We'll do RLE first, and then we'll come back to Huffman tree to finish off in our last sort of 5 minutes. So let me grab another piece of paper. Should have one somewhere in here. Running out of paper. Let me grab a piece from over here. Okay. So RLE compression. If we've got A, B, 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 C, 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 we could compress that to 3A, 3B, 1, 2, 3, 4, 5C. So what it's saying is we can represent RLE in frequency pairs, and we can then represent that as that value. You can do it with zeros and ones as well. So if you had 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, we could represent that as 4, 0, 1, 2, 3, 4, 5, 6, 7 ones. And it's just as simple as that. There is nothing complicated about that. It's just to record the frequency and reduce the amount of data that we're storing by representing it that way. You can represent it sort of with brackets and things like that to make it easier to read, for the examiner to read. But as long as you're counting up the bits right, don't make the mistake of counting up the bits wrong. that can kind of save you save you some trouble and get you some decent marks very, very quickly. So that's RLE. The last one then is Huffman tree. And I'm going to do a very, very quick Huffman tree just for the last 5 minutes, just to take you through. If we, I'm going to do a very quick banana cake. Okay, we have a word that looks a little bit like this. We want to compress it using a Huffman tree. First thing that we need to do is work out the frequency of how many times these letters appear. So down the left-hand side, I'm going to write out how many times they appear. So I've got 1B, I've got 1, 2, 3, 4, 5, 1, 2, 3, 4 A's, I've got 1, 2 N's, I've got 1 C, I've got 1 K, and I've got 1 E. So I've got my frequency across the bottom there. Then I'm going to write it out right to left. The biggest over this side, one of those, and then it doesn't really matter the order after that because they're all ones, like so. Then I can start connecting these together. So you start off always in a Huffman tree with the smallest values first. So K and E, we can then write that as KE2. So I just write it out in that way so you can just make sure you know what you're connecting together. B and C can then go together because they're 2 1s, and then that's 2. Now that one's a 2, that one's a 2, and that one's a 2. So we could connect those 2 together. We could connect those 2 together. I'm going to keep it nice and tidy, so I'm going to connect those 2 together. B, C, K, E, 4. So we've got a 4 here, we've got a 2 here, and we've got a 4 there. So I'm going to keep it nice and tidy, and I'm going to make this nice and simple, and I'm going to do that. I'm going to do N, B, C, K, E, 6. And then I know that this last one, A and everything else, then should represent 10 characters. Now, what I have done, and I've just realized in this one, is I've forgotten the space. And technically, we should put the space in as well. But for the purpose of this, we'll just kind of skip past this. Check, we've got 10 characters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, that's great. So we know we've done that right. We've drawn out our tree, and we've got our, we've made the tree up to the top. We then put zeros and ones on our branches of our tree. So 0 on this side, 1 on this side, as we go through our tree like so. And then that represents sort of the branches of our tree. We can then follow these branches down, and we can work out what the values of each of our letters are. 1, 1, 1, 1. For that one, 1, 1, 1, 0 for that one, and so on and so on. 1, 1, 0, 1. 1, 1, 0, 0. 1, 0, 0. What you should end up with, if you've done it correctly, is you should end up with the smallest amount of bits, which is here. That's a single bit representing the most amount of characters. So every time we see the letter A, it's represented by the letter 0. That's correct. That's great. What we then need to work out is how many bits in total it would take to store our words. So what we could do is write them all above. So it'd be 1, 1, 1, or 1, 0. Write that in there, and then an A is represented by a 0, and an N is represented by a 1, 0, and we could do this all the way along, and then we can add up the number of bits, which we can do just to prove this works. A is 4, no, 0, K is 1, 1, 1, 0, and E is 1, 1, 1, 1. So we can now count up the number of bits: 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So it takes, if we're using Huffman compression, we've got 24 bits to represent this character set. And you can do this another way as well. You can take the frequency and times it by the number of bits. So 1 times 4 is 4. 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 2 times 2 is 4. And 1 times 4 is 4 as well. Which makes it all 4s, interestingly. But so that's 4, 8, 12, 16, 20, 24. So it works that way as well. Might be a bit quicker if you've got a really long sentence at the top. If not, you can just write it out and count it up as well. So we know that using Huffman tree, it's 24 bits. Now, what it says in the spec, if I come back and grab the spec under data compression, you need to know the number of bits required to store a piece of uncompressed data in ASCII, and then maybe compare it with what it is if it has been compressed. So over this side here, if this was stored in ASCII, we would assume that every letter is represented by 7 bits. So if it's represented by 7 bits and we've got 10 characters, we know that in ASCII, it is represented by 70 bits. Whereas using our Huffman tree, it's represented by 24 bits. So then that means if you want to do a quick calculation, and it might ask you this to do this in maths, you have saved 46 bits by using a Huffman tree. You need a dictionary and other things to be able to store those letters in and stuff, but for the purpose of the GCSE, you can then work out how many bits you've saved by doing that process in there. And that is a Huffman tree and how a Huffman tree works. And that is the contents of the data representation chunk of the spec. And we've gone through the whole of the GCSE spec in there. Hopefully that should make you a little bit more confident in the stuff that you need to do. There weren't any questions this evening, which is absolutely fine. If you need to watch that back, it will be available online after it's finished uploading. Otherwise, have a great rest of your evening, and I will see you in a couple of weeks where we will do another topic. I'll let you know in class which topic we're going to go on to, but I'm going to try and do one of these for pretty much each chunk of the spec, so you can go and watch them all. Thank you very much for watching. Have a lovely evening.